Hi, a very good day, I bid to one and all. My name is Tang Kaya. My metric number is 184715. Now, I would like to discuss the topic of joining process, brazing, and soldering in PHY 4207, Materials Processing Technology. For joining processes, brazing and soldering are joining processes that use a combination of heat, filler matter, and typically a flux to join many similar and dissimilar materials. The essential difference between brazing and soldering is the melting temperature of the filler matter. Brazing filler matters melt above 840 degrees Fahrenheit or 450 degrees Celsius, while solder filler matters melt below that temperature. In all cases, filler matters melting temperatures are below the melting temperatures of the work pieces being joined. Joining is accomplished by the flow of the filler matter between closely fitted joints ranging from 0.001 to 0.005 of an inch or 0.025 to 0.13 of a millimeter in brazing to 0.003 to 0.006 of an inch or 0.08 to 0.15 of a millimeter in soldering. The result is a joining of the parts by capillary actions as the liquid filler matter exhibits a stronger attraction to the base materials than itself. A common term for capillary actions is wetting. To facilitate this wetting action, a fluxing agent is commonly employed. The flux lowers the molten filler matter surface tension and inhibits the formation of oxides between the joint surfaces and the filler matter. However, flux residue is corrosive, requiring a separate post-joining cleaning operation. Soaking in hot water or wire brushings are two common methods. Along with joint clearances, proper joint designs are critically important to successful brazing and soldering. The primary joint types employed are the lap joint, the flank lap joint, the butt joint, the flank butt joint. Then, for proper brazing and soldering, joint cleaning is especially important. Grease, paint, rust, and any other impurities must be removed. This may be accomplished by a variety of either chemical or mechanical methods. Brazing is a joining process and has certain advantages over mechanical fastening and welding. Those advantages include the joining of dissimilar metals and materials. Variety material can be brazed which would otherwise be damaged by welding. Inaccessible joints can more easily be brazed. Brazing is also easily and more economically automated than many welding processes. Most ferrous, non-ferrous, and many carbides and cements can be joined by brazing. Fluxes used in brazing consist of fluorides, chlorides, borax, fluoroborates, alkalines, wetting agents, and water. The flux may be in the form of pastes, powders, liquids, and performs and are applied by a variety of methods. Fluxes, especially when heated, can be toxic, so adequate ventilation and safeguards are required. The most common filler metal used in brazing include aluminum silicon, copper phosphorus, magnesium, silver, and nickel alloys. Each of these flow at specific temperatures and are available as wire, foil, paste, powders, and preforms. Filler metals typically have significantly different compositions from materials being joined. For this reason, their selection is critical to successful brazing. There are a few common brazing methods. First, torch brazing. It uses an oxy-fuel gas on previously fluxed joints. It usually in a manual operation but can be automated. Next, furnace brazing. It is a high production method where fixture parts preloaded with filler metals and, when needed, flux are put in a furnace. The furnace may be either a single batch model or a conveyor model for continuous brazing. Besides that, deep brazing. The assembled parts are typically dipped in a heated chemical bath which serve as both fluxing agents and heat source to melt pre-applied filler material. Another one is induction brazing. It is a process that uses inductor coils to induce an alternating current and around a pre-assembled part. The electrical resistance of the part generates the heat to melt the filler metal.
Soldering is one of the oldest methods of joining metals. Because filler metals melt at low temperatures, there is a minimum part distortion and heat damage to sensitive parts. Many combinations of metal to metal, ceramic to metal, and glass to metal may be joined. Soldering is used extensively in the electronics industry, where its limited mechanical strength is not a major factor.
Fluxless for soldering fall into three categories: the inorganic exit fluxes, organic fluxes, and the rosin-based fluxes. These are available as liquids, powder, paste, solid, and in flux core wires. Soldering fluxes may also be toxic and corrosive and require post-cleaning operations. Filler materials include combination of tin lead, tin silver lead, tin zinc, silver copper zinc, and zinc aluminum alloys. Again, as with brazing filler metals, solders are supplied as wires, foil, sheets, paste, preforms, or as bars and ingots. Iron soldering is the oldest and simplest soldering method and is still widely used today. Soldering irons have copper tips which easily stores and transfers heat to the joint. Wave soldering is a specific method used in fabrications of electronic components and printed circuit boards (PCB). In this method, continually circulating fountains or waves of solder are lifted into contact with the joints. As only limited sections of the PCB are immersed in the solder, excess heat and distortion is controlled. Due to the high speed of process, flux and vapor entrapment is reduced. Wave solder machines are highly automated, being able to flux, preheat, solder, and remove flux residue on continuous conveyor.